In this video, we are going to be talking about the production of X-rays. Okay, now there's a diagram on the board in which we are going to use in understanding how X-rays are being produced, what they are used for, and some few properties of X-rays. Okay, now X-rays was discovered by a scientist named Roentgen. Okay, but then the first X-ray was being produced by a scientist named William Coolidge. Okay, his name is William, or rather was Williams Coolidge. Okay, this was his name. Now, hence, this tube is also called the Coolidge tube. Okay, so anytime you hear an X-ray tube, it is also called a Coolidge tube. Now, there are various unlabeled parts of this diagram which you are first going to label. Okay, and then we can now talk about how each of these parts functions. These two parts, they represent ammeters. Okay, these are ammeters for measuring the currents. Okay, these are ammeters, this is a resistor, hence creating a rheostat on that part. Okay, now we are having the cathode. Okay, this one that looks like a funnel is called the cathode. Okay, now it is this cathode that the electrons are being produced. First of all, you should first of all take note that X-rays are produced when electrons that are moving at high speed hit a target. So the electrons are going to move from here and then hit this target. So this is the cathode, and the cathode is usually made of tungsten. Okay, the cathode is usually made of tungsten. And then to get a copious amount of electron, or the maximum amount of electrons possible, we usually coat this tungsten. Okay, why we coat this tungsten to get a very high amount of electron? But what do we use to coat it? We usually use barium oxide. Okay, barium oxide is a compound that is used to coat the tungsten at the cathode for a Coolidge tube, or in the production of an X-ray. Okay, and over here we have a high voltage. Okay, the reason why we have a high voltage is because you notice that the negative part is connected to this terminal and the positive part is connected to this terminal, so it means there will be a potential difference in between here. Okay, this one is the cathode, which is the negative terminal, and this one is the anode, which is the positive terminal. Since there is a potential difference between these two terminals, it means when electrons are produced at this point, they'll be accelerated to the other points. Okay, because this one is positive, when electrons are produced here which are negative, they'll be accelerated to this point. Okay, now this shield they are having here is called a focusing shield. Okay, okay, a focusing cup rather. You see, it is shaped like a cup. Now the reason why we call it the focusing cup, this thing we're having here, this block we're having here, is because when the electrons are being produced, what it does, it helps to deflect the electrons from other directions and then focus it on the target anode. Okay, this is the target anode. Okay, this is the target anode. This block here, this small block here that is embedded in this big one, is called the target anode. Okay, so what this focusing cup does is that it helps us to focus electrons on the target anode. Okay, now inside of this tube is where we have a vacuum. Okay, inside of this tube we have a vacuum. Now why do we have a vacuum? First of all, a vacuum is a region in which air or any other gas has been evacuated. Okay, so we remove the air inside of this tube. So the reason why we can see inside is because it's a glass. Okay, this tube is a glass. Now we remove the air inside so that when electrons are moving or traveling through this space, they get to have the highest amount of energy. That is why reducing the number of air molecules inside there, because if there are air molecules inside, electrons will not just be smashing this target, but rather they will also be smashing the air molecules, thereby reducing the energy, and we won't get the maximum energy of the X-rays we are trying to produce. Okay, so inside of this tube is an evacuated chamber or a vacuum, so we've removed the air, and we usually maintain this tube at a pressure of about 10 to the power of -6 millimeters of mercury. Okay, the pressure inside here is so low that it is about 10 to the power of -6 millimeters of mercury. Okay, now how the X-rays work is that we supply a DC current to the filaments, okay, just like thermionic emission, okay, a DC current to the filament, either we use a DC current or use a low voltage AC, okay. So I'm going to come here and write low AC or DC, okay. We're going to have a low AC or a DC. That is what we do, okay. So what happens is that as this filament or as the cathode is being heated through thermionic emission, electrons start moving from this terminal down to the target anode, okay. Now this target anode, you notice that it is not straight. It is placed at around 45 degrees to the vertical and to the horizontal, okay. 45 degrees to the vertical. The reason why we do that is so that as the electrons, fast moving electrons, strike the anode, they don't bounce back to where they are coming from, but rather they'll be moving in a direction that is perpendicular to it. So the electrons tend to move in this direction after striking the anode, okay. They move in this direction, okay. That is what we do. And then you notice that this whole experiment, we're not just performing it like that, okay. The reason I'm drawing this like this is because so that we can see what is going on inside of it. What we do is we embed this whole device inside of a lead tube or a lead structure, okay, a structure that is made of lead. This is the reason because these x-rays usually have energy, and sometimes they can interact with the human tissue, and when they interact with the human tissue, they cause damages, okay. Not all x-rays cause damages though, but then there are two kinds of x-rays. We have the hard, we have the soft. Also, we can also classify x-ray as the bremsstrahlung x-ray or the continuous or white x-ray, and also we have the kind of x-ray that are called the characteristics x-ray. We are going to talk about all of this, but first let's understand how the x-ray works, okay. So when a low AC current is passed through the filament, it hits it through thermionic emission. So electrons that are fast moving, they move and then they strike this anode. Once they strike this anode, they now start moving in a direction that is perpendicular, okay, producing x-rays, okay. Now x-rays actually overlap with gamma rays in the electromagnetic spectrum. The only main difference is that x-rays are being produced in a Coolidge tube or in an x-ray tube, while gamma rays are produced from unstable nucleus. That is what happens, okay. Now, how are these x-rays being formed? Let me explain. As these electrons, fast moving electrons, strike this anode, they interact with the electrons of the atoms in this anode, that is in this tungsten filament, okay. This small embedded material here is a tungsten filament, okay. It's a tungsten filament, okay. This embedded structure is a tungsten filament. They interact with the electrons of the tungsten filament. Now, how do they do that? When they hit the electrons of the tungsten filaments, the ones they hit are the ones of lower energy. The electrons coming from here hit the electrons of lower energy in this tungsten filament. When they hit the electron, they knock it off. So immediately they hit the electron here, they knock that electron off its particular orbit. But take note that the electrons that they are hitting are the ones of what now? Low orbits. Okay, when they hit those ones of low orbits, an electron in a higher orbit now comes down to fill that space. Okay, I've talked about this thing on the Bose model, so if you need more explanation on that aspect, you can go on and watch our video on Bose model. Okay, so when they hit this filament, what happens is that the electrons are being knocked off, okay, from the lower orbit, and then the one with the higher orbit comes down to fill it. Now the one with the higher orbit has more energy, so when it comes down to fill it, some energy needs to be given off, okay. Those energy are given off in form of what now? X-ray energy. That is how these x-rays are being produced, okay. Now this scenario I just explained is what we call a type of x-ray that is being produced, known as the characteristics x-ray. So for this first case I just explained, the kind of x-ray that is being produced is called the characteristics x-ray, okay. That is how characteristics x-rays are formed. On the other hand, x-ray can also be formed in a different way. How? It is not all the sometimes it is not all the electrons, that is the incident electrons coming from this heated cathode, that strikes the electron on this anode. Some of the electrons can actually escape, that is, they just pass through the orbits which is the place where we find the electrons. They pass through and then they start approaching the nucleus. Okay, now when they approach the nucleus, they hit the nucleus, and then sometimes they even try to escape through the nucleus. To tell you how the energy coming from this cathode is so high from the electrons. Okay, because in this place we use a high voltage, so we want to give them the highest acceleration as possible. So most times we use around 20 kV. Okay, we use about 20,000 volts. So the electrons, once they pass through the orbit where you're having the electrons, okay, these are the incident electrons. Okay, now when they pass through the orbit where you're having the electrons on this anode, what happens is that they approach the nucleus, and even when they get to the nucleus, some of them they manage to pass it, although some of them are stopped. Okay, now majority of the times they are stopped by the attractive force. Remember, the nucleus contains protons. They are stopped by the attractive force of those protons. Okay, now when they are now completely stopped inside of the nucleus, okay, because of the attractive force, they also have to what now? Release energy, right? Now that energy, or the kinetic energy they had initially that is being released, is still a form of light, okay, or X-ray energy. Okay, and the energy, which is the X-ray energy, we are going to call HF. Okay, E equals HF is the difference between the initial energy of the electrons and the final energy. So we're going to have the initial energy minus the final energy. Now take note that it's actually the same formula for both X-rays. Okay, so when we produce the characteristics X-ray, this is formula we use in solving for it. Okay, and then we are going to produce a different kind of X-ray called the bremsstrahlung X-ray. Okay, bremsstrahlung is a German word. I'm going to write it here. Okay, it is called the bremsstrahlung X-ray. Now, this X-ray is also called the polychromatic X-ray or continuous or white X-ray. So either I call it the bremsstrahlung X-ray or I'll call it the polychromatic. Okay, the polychromatic X-ray, or we call it the white X-ray, or we can call it the continuous X-ray. Okay, so we can either call it any of these names. Okay, so depending on how the electrons, that is the incident electrons, interact with the anode, we can create two kinds of X-ray. We can either get the bremsstrahlung X-ray or we can get the characteristics X-ray. Now I also did mention of two kinds of X-ray, right? Now I said that there were two kinds of X-ray. They had the hard and the soft X-ray. Now depending on the accelerating voltage through this system will depend on the kind of X-ray we are going to get, if it's a hard X-ray or a soft X-ray. But before I do that, let's talk about the energy conversion in this system. Now, for the energy conversion of an X-ray, what we notice is that first things first, there is a current that is coming into the system. Okay, now when the low AC current, okay, or a DC current is passed through, which is first electrical energy, so the electrical energy of the current is then converted into heat energy. Okay, that is through thermionic emission. You should know that thermionic emission is the reverse of the experiments that Albert Einstein performed, which he used incident light rays to hit a metal. Okay, and you notice that electrons were being emitted. That is what we call the what now? The photoelectric what now effect. So the thermionic emission in this case is the reverse of the photoelectric effect, or we can say that the production of X-ray is the reverse of photoelectric effect, simply because for X-rays, electrons hit the target producing what now? On the other hand, for photoelectric effect, light is going to hit a target producing what now? Electrons. So you see they are the reverse of each other. Okay, so from the electrical energy, it is being converted into heat energy used in heating this cathode rather that we're having here. Okay, so we are going to have from electrical energy through the current, electrical energy, we are going to get heat energy. Now this heat energy is used to accelerate the electrons. Okay, now these electrons, they have what now? Energy too, which is called the kinetic energy. From this energy we get to the kinetic energy. Okay, we're going to get to the kinetic energy, and then the kinetic energy immediately the electrons smash this box chamber that we're having here. Immediately they smash it, about 99% of their energy is being converted into heat. Okay, that is why we are having these cooling fins here. You can see these fins that we're having here. Okay, they are called the cooling fins. Okay, they are used in cooling this anode, simply because the electrons that are coming, they have very, very high energy. So 99% of the electrons are of their energy is being converted into heat, okay, in this copper chamber. This is the copper. The reason why we use copper is because copper has a high thermal conductivity, so it can absorb much heat, okay, which is being cooled by these cooling fins that we're having here. Okay, so from electrical energy converted into kinetic energy, and then they are now used to produce the what now, the X-ray, which is the X-ray energy. So I'm going to call it the X-ray energy. Now this is the energy conversion in the system of an X-ray, okay, of an X-ray. Now how about the two kinds of X-ray that are being from the hard or the soft X-ray? We just talked about the energy. Okay, now some X-rays have very, very high energy. Okay, that is why we embed this system in a lead chamber. The reason why we do that is so that X-rays that are flying in another direction, there is no way we are going to have a complete vacuum here. There is no way we are going to have a complete vacuum, simply because even if we remove as much as possible air we can remove from inside of this tube, there will still be tiny amounts of air particles found in it. So we assume that the electrons can also hit air particles, changing the direction. Instead of this perpendicular direction we wanted, changing the direction into other direction, which could actually interact with the human body, okay, and causing damages to tissue. So most times we even place an aluminium foil, okay, at this point. We place an aluminium foil at this point, okay, and an aluminium thin sheet at this point, so that X-rays of low energy can be absorbed. We only want the ones of high energy. The ones of low energy, they can be stored by the human tissue, causing damages. But the ones of high energy, they will just pass through and continue. But we don't want them to stop in the human tissue. So we place an aluminium foil over here so that when the X-ray hits the aluminium foil, what they do is that if they are having low energy, they'll be stopped by the aluminium foil. But they are having high energy, they can just what now pass through directly, making use of them. Okay, that is why we have two kinds of X-ray. So the ones of low energy, okay, the ones of low energy. So an X-ray which is having a low energy is what we call the soft X-ray. These ones basically don't have applications, or if they do, maybe in the future they will. Okay, but the ones we use or in radiography most times is the hard X-ray. Okay, so we are having the other kind of X-ray, which is the hard X-ray. Now the hard X-ray is the kind of X-ray that has high energy. Okay, so these ones have high energy. So for low energy we have soft X-ray, and then for hard X-ray they are having what now, a very high energy. Now, how do we now increase the energy of this X-ray? We can increase them by increasing the accelerating voltage between these two chambers, okay, or these two terminals, the cathode and the anode. Now, if we can increase the voltage between these 2 points, it means we can increase the velocity or the kinetic energy of these electrons. And the higher the kinetic energy, the higher the force they use in hitting this guy, producing what now, a high energy what now, X-ray. And we can do that by increasing the voltage. If we can get as high as much voltage as we can get, we are going to get what now, a high energy X-ray. But if it is low, most times usually less than 20 kV, we get what now, a low energy X-ray, and that is something we do not want most times. Okay, now a high energy X-ray is actually an X-ray that has a high frequency. Here is the formula I derived as well, or I wrote as well. E is equal to HF. So if this energy is to be very high, H is a constant, which is 6.62 times 10 to the power minus 34 jouleseconds, Planck's constant. Okay. Now, frequency still needs to be high. You can also say that the energy depends on the frequency. So a good or a high energy X-ray is actually an X-ray that has a high frequency. Okay. So we want to produce as much X-ray that has a very high frequency, or otherwise an X-ray that has low wavelength. Okay, that's what we want to do. So a good X-ray is one that has high frequency and low wavelengths, okay, or high energy. So this is how X-rays are being produced, okay, using a Coolidge tube or the Coolidge chamber. It is very easy, and in our next few videos we'll talk about the other kinds of production of X-rays and the likes. Now if you have a question, do it to put it in the comment section. And if you did learn or enjoy this video, please smash the like button. It will help us to create more video, and then it will help us to know that you're actually learning from these things and inspire us to create more for you. Okay, in our next few videos that will be uploaded, You might want to be one of the first persons that will get notified about it. So click on the notification bell, of which you cannot do that if you have not subscribed, okay? So do it to subscribe to the YouTube channel. The name remains Dr. Flash. See you in the next video. Bye.